explained the three position synthesis for path generation and function generation, we can attempt to solve another problem by a two-stage synthesis. Suppose the problem is as follows. We have to design a 4R linkage such that the coupler curve is approximately a straight line. We talk of three position synthesis. Obviously, that problem we could have done by the method explained earlier. Here what we are doing, we are saying it is not only a three position synthesis for a coupler curve which is approximately a straight line, we also want to coordinate it with the input movement. That means that as the coupler point goes from first position to second position, the crank must rotate by a specified amount. Similarly, as the coupler point goes from the second to third position, we want the crank to rotate by again a specified amount. To solve this problem or coupler curve generation, of course, an approximate straight line coupler curve generation coordinated with the input movement can be solved in two stages, which will be explained now. To solve this problem, first we design a slider crank mechanism. This is the slider crank mechanism such that this pair of coordinated movement from first to second configuration and second to third configuration can be designed. This we have done just now. If we specify theta 212, theta 223 and the corresponding S12, S23, I can always design this slider crank mechanism. After designing the slider crank mechanism as a function generator for two pair of coordinated movements, what we do, we talk of the midpoint of this connecting rod. At the third configuration, say it is here. At the second configuration, the same coupler point, same midpoint of the connecting rod is here, and in the first configuration, it is here. So we mark this midpoint of the connecting rod corresponding to the three specified configurations as C1, C2, and C3. The center of the circle passing through these 3 points C1, C2 and C3 is here. So what we do, we make that as our O4 for the required 4R linkage. For that purpose, we remove this slider and take this fourth link and put a hinge between that midpoint of the original connecting rod connected by this rigid link whose center is at O4, which is hinged at O4. This is the other fixed hinge. So we have got a 4R linkage, namely O2, A, B, O4. This is designed from the previous slider crank, only the slider has been removed. Now if we move this linkage, what we should see, that this point of the coupler is still following the original straight line, but only approximately. We can notice this, that this coupler point, though not guided by the slider as before, the slider is totally detached, but this 4-bar linkage is also driving this coupler point through the axis of this slot where the previous slider was moving. So we have generated a coupler curve synthesis problem or path generation problem coordinated with the input movement. As it goes from position 1 to position 2, this rotates by a specified amount. As it goes from position 2 to position 3, again it rotates by the specified amount which was dictated by the original slider crank. So this is what we call a two-stage synthesis. So all the methods that have been taught so far can be cleverly used to design more complicated mechanisms, rather mechanisms with more complicated motion requirements. Let me now repeat this two-stage synthesis problem. What we did, first we designed a slider crank mechanism such that it acted as a function generator. The slider displacement was coordinated with the crank rotation. Then we took the midpoint of this connecting rod at these three configurations, which is C1, C2 and C3, for the three positions which have been generated by this slider crank as a function generator. Then we removed the slider and consider the midpoint of this connecting rod. Corresponding to these 3 positions, it is at C1, C2 and C3. The center of the circle passing through these 3 points is at O4. So we added a 4th link with O4 as the fixed hinge and connecting it with C1. So we get a 4R linkage with this coupler point generating an approximate straight line as we have seen earlier. And as it goes from position 1 to position 2, the movement of the crank is exactly same as it had with the slider crank. Similarly, the movement of the crank from C2 to C3 is again theta 2, 3, which is coordinated. Now the question is, why did I take the midpoint of the connecting rod? I could have taken any point on this connecting rod and consider the 3 positions of that particular point and think of the circle. This is the model of the proposed 6-link mechanism to be used as a forklifter consisting of only revolute pairs. As we see, there are the body of the truck is the fixed link or link number 1, then there is link number 2, 3, 4, 5 and 6. And as this input link of the crank is moved by a motor, what we see, that fork, that is this link number 6, moves up and down almost vertically. But this vertical movement is without any vertical guide. We will try to design this problem such that these 2 fixed pivots are located on the body of the truck at convenient positions, and we have to come up with this link length such that the rotation of the crank is converted into almost vertical movement of this fork. We will solve this problem by what we call a multi-stage synthesis. Let me now pose the problem with the required design specifications. Let us any vertical guide. Let me now summarize this multi-stage synthesis of this guideless forklifter as we have completed in today's lecture. We have chosen first O2, this is this fixed pivot at a convenient location of the body of the truck. We have also chosen a vertical line in front of the truck which is convenient for the movement of the fork. So first we design O2AB as a slider crank such that the slider movement at B is coordinated with the input motion of the crank. 60-degree counterclockwise rotation of the crank has caused 1.5 meter vertical travel of this point B using 3 Chebyshev accuracy points in this interval. Next, we chose O4 conveniently on the body of the truck. Then removed the slider and got a coupler point here at C such that O2, A, C, O4, this 4R link has a coupler point B which has an approximate straight line path, and the movement along that straight line path is coordinated with the motion of the input crank. In the third stage, we had chosen this point D again conveniently on the body of the fork such that a second point is guided along the same vertical path. After choosing this point D, we found the inverted positions of the D corresponding to the second and third configuration, holding this link, that is link number 4, fixed at its first configuration. And the center of the circle passing through these 3 inverted positions of D, namely D11, D21 and D31, I found the center of that circle at this point, which I called E. Finally, we get this 6-link mechanism where I have a forklifter without any vertical guide. So the techniques that we have learned for function generation, motion generation and path generation can be synthesized together to have a multi-stage synthesis problem for even more complicated problem. So in today's lecture, we have designed a 6-link forklifter using only revolute pairs by a multi-stage synthesis process, which are basically combination of the 3-position synthesis for function, motion and path generation of 4-link mechanisms, which we had discussed earlier. In our next lecture, we will try to design another 6-link mechanism for a railless garage door, a garage door which is required. Let us now study the model of this proposed 6-link mechanism. This is the door board, which is horizontal parallel to the roof of the garage when the garage is open. And by driving this mechanism, we can close the garage and the door board becomes vertical. If we see the movement of this garage door from this open to the closed position, what we should note that the garage door board is not interfering with the car that is kept inside, and the car is quite a high car. Thus, the motion of this garage door board is almost horizontal and then suddenly falls to the vertical position. And such a movement is not possible by using a simple 4-link mechanism with this as the coupler, the door board as the coupler. So we go for this 6-link mechanism. And now we shall give the details of the design of this 6-link mechanism and determine all the kinematic dimensions by applying the multi-stage synthesis procedure that we model. Let us look at this model of this 6-link dual mechanism. This link number 2, 3 and 4, as I said, constitutes a 4-hour linkage, and this is the coupler point C. And there is a prismatic pair between this link 5 and the output link 6, which is hinged at this point, which we earlier called O6. This is O2, A, B, O4, C and O6. As we give continuous input rotation to this crank rocker linkage, what we should notice that during this portion of rotation of the crank, during this interval of the rotation of the crank, the output link hardly moves, because this coupler point goes along a fairly good approximation for a straight line. And as soon as this comes out of the straight line portion, the output link starts moving, and this is the maximum position, rather the extreme position of the output link when this line becomes tangent to this coupler curve. Our job is to design these linkages using the method of point position reduction, and we shall use first we shall design a 4-link mechanism with 4 points on this coupler curve, namely C1, C2, C3